It is part of the mathematical folklores that integration is analogous to taking sums, and the differentiation is like taking differences. This is the core principle behind the fundamental theorem of calculus, which says integration and differentiation are inverse processes of each other, just like addition and subtraction. However, few textbooks explain this point explicitly, that calculus is just generalization of ordinary pluses and minuses from finite domain to continuous infinite. The purpose of this lecture is to make this analogy as clear as possible, since many difficulties one encounters in studying calculus become easier when discretized. The biggest difference is in continuous domains. There is no concept of the neighboring points, only neighborhood around a given point. Humans are finitary. We only know how to perform discrete operations. To expand into the continuum, one needs to introduce the concept of infinitesimal, which should be thought of as almost zero, but not quite. Then take limits. Given a graph of function fx from, say, real numbers to real numbers, and 2 points on x-axis a and b, a definite integral is the area under the curve of f between lower limit a and upper limit b, denoted as integral sign from a to b fx times dx. Before Newton, the best way people knew how to compute these was using rectangles as approximations. Here is an example of how this is done. Take fx as x squared, a equals to 0, b equals to 2. We want to compute this integral, which is the area under the orange curve between 0 and 2. To estimate, let's start with 4 rectangles, each of width 0.5. For my own convenience, I will set the heights of these to be the value of the function on the right side of the rectangles. So this is an overestimate. One can make other choices, but the end result is the same once we take limits. The computation steps are summarized in this table. First column is index I, which labels the rectangles. Column 2 is independent variable x at half integers by our choice. Column 3 is the function value x squared, which we set to be the height of the rectangles. Column 4 is column 3 times 0.5, i.e. height times width, so equals to the area of each rectangle. Column 5 is the cumulative sum of areas of 1 to n rectangles from column 4, i.e. the estimate of integral from 0 to b. When b equals to 2, it corresponds to I from 1 to 4, giving the sum 3.75, which is the sum of these 4 numbers. We usually express these in sigma notation. Sum I equals to 1 to 4 xi squared times 0.5. While for a general function f, one writes this sum as sigma I equals to 1 to n f xi times delta x, height times width. Thanks to Newton and Leibniz, we now know the integral of x squared from 0 to any number x is x cubed divided by 3, so we can read off the exact value 2.667 from column 6. Our approximation is not great. The main issue is that the rectangles are too wide. To better follow the curve, we need to use thinner, therefore more rectangles, like these. Recall, this is what we just did using 4 rectangles. For comparison, the bottom graph and table are using 10 rectangles, each of width 0.2. Repeat the steps, we get 3.08, much closer to the true value. As one uses more thinner rectangles, the estimation gets better, but computation also gets more tedious. Anyway, all these sums are still only approximations. Usually, we arrange them into a sequence based on increasing n. To obtain the exact answer, we need to take the limit as n goes to infinity. It is in this sense that integral resembles summation. One can think of integrals as sums of infinitely many rectangles of infinitesimal width dx. Integral sign is like sigma. 1 to n becomes a to b. Delta x turns into infinitesimal dx, which is almost zero, but not exactly. Clearly, our table method is not ideal. We need a better way. Around 1670, Newton and Leibniz demonstrated the fundamental theorem of calculus and showed that integration is an inverse process of differentiation, therefore gave us an algebraic solution for many classes of integrals. Differential of a function f at a point x, by definition, is the slope of the tangent line to the curve at x. Now 2 points determine a line. Here, we only have 1 point x. The idea is to take another point nearby, say h unit away. Draw the second line through these 2 points. The key figure is this right triangle. The slope of the line is the height of the triangle, delta f, over its base, delta x. This is how subtraction comes into the picture, since delta f is f x plus h minus fx, the difference in y-coordinates of these 2 points, while delta x is x plus h minus x, the difference in x-coordinates. Let's take f to be x cubed to be concrete. We expand delta f into a polynomial in h and divide by delta x to obtain this expression. As we let h go to 0, the second point gets infinitesimally close to x. The second line becomes the tangent line. Delta x, delta f both approach 0, i.e. become infinitesimal. The triangle becomes infinitesimally small. But the slope delta f over delta x remains finite and tends to a definite value 3x squared as all terms containing h become 0. This is the differential we want. Notice it only depends on the point x and its infinitesimal neighborhood. So our formula works for any x. We essentially made a new function from f called its derivative or differential by assigning to each point x slope of the tangent line at x. We usually denote the derivative as f prime, or even better, using Leibniz notation, df over dx or dy over dx, because it is the limit of a ratio. It is also convenient to use a pair big F prime equals to small f to emphasize the relationship between the 2 functions, as we have been using big F equals to x cubed and the small f equals to 3x squared. This example is easy, but the pattern is very general. We express delta f as a polynomial in H. After dividing by delta x equals to H and taking limits, only the linear term in H survives, which is the differential we want. In practice, using this type of calculations, people have built tables for elementary functions and rules for their composites so that we can compute derivatives for all functions we commonly need. For example, the derivative of a constant is 0 because function values don't change. Delta f and df are always 0. The derivative of a monomial x to the n is n times x to the n minus 1. We have been working with n equals to 3. E to the x is the only function whose derivative is itself. E, roughly 2.718, is called the Euler number or the natural number and plays a central role in calculus because of these. There are also rules for how to combine functions. For instance, the derivative of a sum is the sum of the derivatives. Multiplying a constant commutes with taking derivatives. These two rules together make differentiation a linear operation, which really comes from commutativity, associativity, and distribution law in discrete arithmetic. There is also product rule and chain rule. From these, we can deduce everything else. Now, the fundamental theorem of calculus says that, given the function small f, we can define a new function big F equals to integral sign from a to x ft dt. Then big F prime equals to small f. Notice big F is a function of the upper limit. To avoid confusion, we replaced the independent variable for f with t or any other letters you like. It is called a dummy variable because the result of a definite integral is a number, does not depend on the name of the variable. This is the first part of the theorem. Newton and Leibniz established the second, more useful part. If we know a function big F prime equals to small f, then integral from a to b fx dx equals to big F at b minus big F at a. So in order to solve integrals of little f, one just needs to find the antiderivative, also called the indefinite integral big F, and plug in numbers. This is easier said than done though, because inverting derivative tables is usually not as easy. Nevertheless, now we have a systematic algebraic method to deal with integration. So, what does the slope of a tangent have to do with area? Again, it's best to examine the discrete situation first. On the left is the picture of integration. We start with the orange curve, small f equals to x squared, which determines the heights of these four rectangles, each of width delta x equals to 0.5. Sum of the area is an estimate of the integral from 0 to 2 fx dx. On the right is the picture of differentiation. We have the red curve, antiderivative big F equals to x cubed divided by 3. And draw these blue line segments starting from lower limit 0 and connected at endpoints. Together, they form a new function we call scripted f. Each segment determines a right triangle with the horizontal leg set to be at half integers, the same as the width of the rectangles on the left, and the hypotenuse parallel to the tangent at its right endpoint. For example, this piece is parallel to this light blue tangent. This piece is parallel to the tangent line here, etc. Therefore, the slope of each segment is also little f equals to x squared, same as the height of the corresponding rectangle. Thus, the vertical leg equals the area of the corresponding rectangle, as both are fx times delta x. So these two sums are numerically the same. On the other hand, vertical legs delta f are the differences of f at the endpoints, i.e. delta f4 equals to f2 minus f1.5. Delta f3 equals to f1.5 minus f1. Delta f2 equals to f1 minus f0.5. And the delta f1 equals to f0.5 minus f0. To avoid clutter, I didn't draw the first two triangles. Therefore, this sum makes a telescope series, meaning that middle terms all cancel. What's left is simply f2 minus f0, the difference of f between upper and the lower limits. The key is summing areas of rectangles are equivalent to summing differences in f. This is how summation and subtraction are conspiring, so to speak, to turn small differences into a big one. Now, one can use more rectangles and triangles. The pattern still holds. Passing to the limit, we have sum of infinite numbers of infinitesimally thin rectangles on the left, which equals the infinite sum of infinitesimal differences in scripted f on the right, which are exactly f2 minus f0 as the discrete line segment scripted f coincide with the continuous curve big F in the limit. Or from another view, as x changes by infinitesimal dx, the area on the left changes by an infinitesimal amount fx times dx. The function big F on the right changes by infinitesimal df, which is the same magnitude. So infinitesimal area of rectangles are simply measuring infinitesimal changes df, and one can sum or integrate these infinitesimals to compute finite differences. This is the essence of why calculus works, and why some people say calculus is the theory of change. You may be wondering why we don't use the secant lines and their associated triangles like when calculating differentials on the previous slide. This is because we only have small f and are looking for big F. We are cheating in some sense by drawing the curve for big F on the right. It's only meant to serve as a visual aid. All we have are the slopes of the tangents at each point, so we could only construct these line segments. But we could construct them as densely as we want and obtain big F as the limit. Although they are inverses of each other, there are some important differences between addition and subtraction. First of all, one can add as many numbers as one wishes, but subtraction only makes sense for two numbers. After taking limits, differentiation only depends on x and its immediate neighborhood. So it is local, while integration is global, depending on all values between a and b. This is why differentiation is easier in many ways. For instance, we can make the function and its derivative share the same independent variable x without any confusion, while here we have to define big F as a function of the upper limit. Remember, in the tables we constructed to estimate integrals, we could calculate the cumulative sum column 5 for any value n. This is also the reason indefinite integral are only defined up to a constant, since the derivative of a constant is 0. In the picture on the right, we can move the curve up and down by any constant without changing the derivative. In the picture on the left, we can choose different lower limits. Different choices will differ by a constant, which cancels after one plug in values to compute the definite integral. These are some of the ideas one needs to keep in mind when studying calculus. I hope this is helpful.